chi-square testing for true population variance and standard deviation will look like this. For true variance, the possible setups will be sigma squared equals a number versus sigma squared does not equal a number, and this is two-tailed chi-square testing. If you want to do true standard deviation, the setup for a two-tailed is sigma equals a number, sigma does not equal a number. And then for the right-tailed, excuse me, sigma squared is less than or equal to a number versus sigma squared is greater than a number. That's a right-tailed chi-square test. And if you're speaking about true variance, then it's sigma less than or equal to a number versus sigma greater than a number. Again, Connect Math will have the fact that sigma is equal to a number, and the alternative will have that sigma is greater than a number. So that's a right-tailed test, chi-square test. Connect Math. For a left-tailed, you've got the null and the alternative, sigma squared greater than or equal to a number in the null, but sigma squared strictly less than a number in the alternative, and that's left-tailed. For the true standard deviation, it would look very similar. You would have sigma greater than or equal to a number versus sigma strictly less than a number. Again, that's a left-tailed chi-square test. This is for true variance, and this is for true standard deviation. Connect will have that the standard deviation is equal to a number, but the alternative will be that the standard deviation is strictly less than a number. Remember, the new edition of the textbook always has equality in the null hypothesis, which is h sub 0, regardless if it is two-tailed, right-tailed, or left-tailed. I prefer the symbols less than or equal to, greater than or equal to, because some of the word problems use phrases like at most, less than or equal to, and at least, greater than or equal to. The test statistic this time is going to be, and we will also be doing the traditional method and the p-value method. The test statistic formula is this. Remember that this symbol means chi-squared. It's a variable. This is n minus 1 times s squared, which is sample variance, or you could say sample standard deviation squared gives you sample variance. And then sigma squared is population variance, which is going to be our claim, coming from our claim in these problems. We will be able to substitute in for sigma squared. What I do in lecture, you can see that there are quite a few problems here. I say that for the chi-square test for true population variance and standard deviation, if degrees of freedom go beyond 30 with the chi-square table, like 40 or 50 or 55 or 65, go with the closest yet smallest multiple of 10, and I'll show you an example of that. If your degrees of freedom would be 36, you notice that there is not a row 36, so you will go to row 30. Go with the closest yet smallest multiple of 10. So don't go to 40, but go to row 30 if your degrees of freedom happen to be 36. The first three problems focus on finding critical values for a right-tailed chi-square test, a left-tailed, and a two-tailed. And then we do problem number 4 as a traditional method problem. And number 5 is a traditional method problem, and it deals with raw data. 6, 7, and 8 are finding the p-value interval for a right-tailed, left-tailed, and two-tailed chi-square test, knowing the test statistic. And then number 9 is just the p-value method. So I would like to focus on finding the critical values for a problem like number 1. Problem number 1 says, find the chi-square critical value for a sample size of 16 for an alpha equal to 5%, and the test is right-tailed chi-square test. What you would do is you would write down your sample size, which is 16, and that would tell you that your degrees of freedom would be 15 in the chi-square table. Alpha is equal to 5%, and we know this is a right-tailed chi-square test. Notice that it did not say right-tailed chi-square test for true variance or true standard deviation. So I'll just put true variance here, sigma squared less than or equal to a number versus sigma squared greater than a number. That's what a right-tailed chi-square test would look like for true variance, sigma squared. What you have to do is go back to your chi-square distribution and remember its properties from Chapter 7. And remember, they start at 0, and these distributions are positively skewed. And this is the chi-square axis, and it runs out to positive infinity. So 0 all the way to positive infinity would be the axis. Since this is right-tailed, you would shade the right tail. And remember, we are looking for this chi-square value here, which would be your critical value. For the chi-square testing, critical values are always positive. If it's a right-tailed chi-square test, the critical value is positive. If it's a left-tailed chi-square test, the critical value is positive. If it's a two-tailed chi-square test, the critical value is positive. It will always be positive because of this particular type of distribution. Very special distribution. Remember how the chi-square table works, and you will need the chi-square table with you. According to how the chi-square table works, here is a copy. The areas that you look up at the very top of the chi-square table are the areas above the unknown chi-square value on the axis. And in these critical value problems, it's going to be alpha. Therefore, this is alpha. And when we go to our chi-square table, we would go to row 15, and we would look up our given alpha of 5%. Our two fingers would meet at 24.996, and that's going to be your critical value in the right tail, 24.996. And remember, this is the area above the unknown chi-square value, which is exactly alpha in the right-tailed test. Let me write that in the picture. 24.996 is your critical value. Problem number 2. We are told that it's a chi-square test. Sample size is 11, alpha is 5%, and it's left-tailed chi-square test. This is number 1. Number 2. N is equal to 11. Alpha is equal to 5%, and we know that this chi-square test is left-tailed. That would mean that if you had a possible setup for the true variance, it would be sigma squared greater than or equal to a number versus sigma squared less than a number. That's a left-tailed chi-square test for true variance. You would draw your distribution, and this time you would shade the left tail. And you're looking for that positive chi-square value that indicates the left tail. The way this works is that the given alpha is this area, 0.05. That means the area above the unknown chi-square value is 0.95. This time you're going to go to row 10, and you are going to go to the column that says 95% because that's the area above the unknown chi-square value. So alpha is in the left tail and alpha was given to you. Row 10, column 95%. 3.940 is going to be your critical value, and it remains positive. 3.940. 95% is above that chi-square value there. 3.940. And that goes here. Therefore, the critical value is 3.940 for problem 2. And for problem 1, it was 24.996. The next problem, number 3, is a left-tailed chi-square test. Excuse me, two-tailed. Find the chi-square critical values for a sample size of 23, an alpha of 5%, and it's a two-tailed chi-square test. And I'll write that here. Sample size is 23. Alpha is still 5%. Remember, alpha determines critical values, and it's a two-tailed chi-square test. And so that means the null would have equal to, and the alternative would have not equal to, if we're talking about true variance. You would draw your distribution and positively skewed, shade the right tail and shade the left tail. You're looking for this chi-square value from the left and this chi-square value from the right. Each area is alpha over 2 in each tail, 0.025 in each tail. This is kind of like when we did confidence intervals for true population, variance, and standard deviation, those chi-square intervals. You would have to go to row 22, and then the columns you would go to, for chi-square from the right, you would have to go to the column that says 0.025. For chi-square from the left, you'd have to go to the column that says 0.975. And that's because those are the areas that are above these two chi-square values. Chi-square from the right, the area above it's alpha over 2. Chi-square from the left, the area all the way above it is 0.975. And you can find that because that's one takeaway, the 0.025 in the left tail, which is below it, and that's 0.975 above it. Going to the table, I'm going to block off row 22, left finger, and you go to column 0.025, and that is going to give you 36.781 for chi-square from the right. And column 0.975 gives you 10.982 chi-square from the left. So these are your two critical values, and they remain positive. 10.982, 36.781. And I will write those down in the diagram. So go to column 0.025, above the area above chi-square from the right, and then column 0.975, the area above chi-square from the left. And these are your two values. And that pretty much sums up what you would have to do. This one was 10.982, and this one was 36.781. Again, they're both positive. So we have two critical values, 10.982 and 36.781. And they would determine our rejection regions. that pretty much sums up finding critical values for any type of test that you can be given. So let's do a problem. The first problem that I want to do on the sheet is number 4. And we'll do that together. It's in the lecture notes, but we'll also do that together. And I'm just going to do the traditional method for that problem. Sorry about the delay. Number 4. An instructor wishes to see the variation in scores of 23 students in her class is less than the variance of the population. The variance of the class is S squared equals 198. Is there enough evidence to support the claim that the variation of students is less than the population variance of sigma squared equals 225? Use a level of significance of alpha equals 5%. Assume the scores are normally distributed. An instructor wishes to see whether or not the variation in scores, and this is variation, of the 23 students, that's your N, in her class, is less than the variance of the population. The variance of the class is S squared equals 198. Is there enough evidence to support the claim that the variation of students is less than the population variance of 225? Alpha is 5%. Therefore, we know for problem 4 that we have 23 students in the sample. Alpha is 5%, and here's the claim, that the variance of the students, or variation, is less than the population variation, which is 225. And the symbol less than looks like this. So there's your claim. When you go to look for that symbol on your sheet, you would see that less than is going to be a left-tailed chi-square test. Here's your sheet. And even though it has mu, you can still think of that as sigma squared less than. Notice how I'm not using the calculator very much because the calculator is not helpful this time. This is traditional method. Step 1. Sigma squared less than 225 has to be in the alternative, and that's your claim. And then sigma squared greater than or equal to 225 is your null. So it's a left-tailed chi-square test. Step 2 is the one and only critical value, and it's still positive even though it's left-tailed. You draw your chi-square distribution, and you shade your left tail, and this is your alpha of 0.05 in the left tail. The area above it, which is the column you go to, is 0.95, and degrees of freedom will be row 22. So I'm going to go to row 22 and column 0.95 to find that. $22.95. Two fingers meet at 12.338, and it remains positive. 12.338. And I will fill that in. That defines our rejection region from our non-rejection region. Step 3 is the test statistic, and that's n minus 1 times s squared over my claim. That's 23 minus 1, and the paragraph did say that S squared is equal to 198. So that goes in for your S squared. And your claim from the setup here is 225. Sigma squared is less than 225. So that goes in for sigma squared. S squared sample variance was given to be 198, and the claim is that the sigma squared is less than 225. When you plug this into your calculator, you will receive a value of 19.360. And I round to 3 places accurately because the values given in the chi-square table are given to 3 places. Put the 19.360 in the picture, and you will see that it falls in the non-rejection region. So step 4, do not reject the null statement. And the null statement said that sigma squared was greater than or equal to 225. So what does that mean about our claim? If the claim is the alternative that says it's less than, and we're not rejecting the null statement that says it's greater than or equal to, there is not enough evidence to support our claim that the variance is less than 225. If you have to go to the diagram to be able to figure that out, you would put your finger on the fact that the claim is the alternative and we did not reject the null. There's not enough evidence to support the claim that it's less than 225. Going back to the problem and the question, it says, is there enough evidence to support the claim that the variation of students is less than the population variance of 225? You would say no. There's not enough evidence to support the claim. And that was traditional method. Because we decided to not reject the null, the possibility of mistake here is beta, which is a type 2 error. Not rejecting the null when it could be false. Not rejecting the null when it could be false. So beta is the possibility of any type of mistake. Problem number 5 is raw data, and I am going to use the calculator to show you how we're going to do this particular problem. And I will begin by putting the raw data values in the calculator. The number of carbs found in a random sample of fast food entrees is listed below. Is there sufficient evidence to conclude that the variance differs from 100? Variance is sigma squared. Differs means not equal to. Verify that the sample variance is 135.4 approximately. And we'll see that with this raw data. Stat, edit. And you can see that I have data in all of my columns. I'll just go to column L4 to put in these values. 53, 46, 39, 39, 30, 47, 38, 73, 43, and 41. And just go back and check 53, 46, 39, 39, 30, 47, and I made a mistake here. That would be 38, 73, 43, and 41, 10 values. And then we would go to stat, arrow over to calculate one variable statistics. And I tell the calculator I put mine in the L4 column, and I get L4 down here. It's above the number 4. It's in blue, so I press second number 4. You may use column L1 and then calculate. Leave frequency list blank. And the sample mean I don't really care about, but we do need sample variance. Notice that this is sample standard deviation. Remember, to find sample variance S squared, we have to go to second stat, or we could square this S. Type this out and square it, but don't round and square it. Type out this 11.6375828 and square it. But I prefer to go to second stat, and when you go to second stat, arrow over to math, and variance is number 8. And the calculator is saying where's your data, and it's in L4, and I'll close that in parentheses. And so I did verify that it's 135.43 repeating, but since my raw data values are whole numbers, round to the nearest tenth, an additional decimal place, according to Chapter 3. Therefore, you are expected to take raw data and find the sample variance. So again, this is the number of carbs found in a random sample of fast food entrees listed below. And this is 10 different entrees and number of carbs. Is there sufficient evidence to conclude that the variance differs from 100? Let alpha be 5%. So question number 5, alpha is 5%. And our sample size is 10. We just found that our sample variance is 135.4. And the claim, is there significant evidence to verify that the variance differs from 100? Variance is sigma squared. Differs means no longer equal to. So that's what we're testing. So it's a two-tailed chi-square test. And I'm going to go through the traditional method. Is there sufficient evidence to conclude that the variance differs from 100? Step number 1 is the setup, the null versus the alternative. The alternative is the one that says differs, and the null is the one that says equal to. The claim is the alternative this time because it says differs from 100. Step 2 with traditional method would be my two critical values. Therefore, I shade the left tail, shade the right tail. I'm looking for chi-square from the left and chi-square from the right on the axis. Each tail is alpha over 2. So that's going to be 0.025 in the right tail, and the area above it is 0.025, and that's the column we go to. And in the left tail is also 0.025. So the area above chi-square from the left is 0.975, and that's the column we go to. We would go to row 10 minus 1, which is row 9. Degrees of freedom would be 9. And go to those columns, and that's going to give us our two critical values. So row 9, column 0.025 is 19.023, and column 0.975 is 2.700. So here are my two critical values, and both are positive. So area above chi-square from the right, and then area above chi-square from the left. And I'll write those two values in, 2.700, 19.023. Test statistic time. Chi squared is equal to n minus 1 times s squared over my claim. That is 10 minus 1 times s squared, which is 135.4, all divided by 100. When you calculate that, you receive 12.6 19.186 to 3 places accurately. And then you put it in the picture, and 12.186 falls in the non-shaded, non-rejection region, your test statistic. Therefore, step 4, do not reject the null statement. And the null statement that we're not rejecting says that it's equal to 100. If the claim is the alternative that said it differs from 100, and we do not reject the null statement that says it's equal to 100, there is not enough evidence to support the claim that variance differs from 100, no longer equals 100. There's your summary. And to see that in the diagram, in this case, our claim was the alternative, differs from 100. Do not reject the null that says it equals 100. Therefore, there's not enough evidence to support the claim that says it differs from 100. So we're here in the diagram. And that sums up the traditional method here for a two-tailed chi-square test. P-value. P-value intervals are something we're going to have to find with the p-value interval. And that is why I took the time to show you 6, 7, and 8, which would be the 3 different situations that would arise when you're trying to find the p-value interval. You need the test statistic to find the p-value interval, so number 6. Find the p-value interval when chi-squared, which is the test statistic, is 19.274. N is equal to 8, and we know this test is right-tailed. It's a right-tailed chi-square test, either for variance or standard deviation. I think I'll write down what it would look like for standard deviation. Sigma is less than or equal to a number. Sigma is greater than a number. And this is the test statistic. You will go to row 7, and you will look across that row and find the 2 values that bound the test statistic. So let me isolate row 7. $19.274 is the test statistic. And you see that it falls between the last 2 values. 19.274 test statistic. What you do is you go to the top and you cross fingers. 0.005 is smaller than 0.01, so that's why I say cross fingers. Since this is a right-tailed test and you're on the right side of the table, your p-value interval will look like this. So there's the p-value interval for question number 6, 0.005 to 0.01. Question number 7. It says find the p-value interval when the test statistic is 3.823, sample size is 13, and it's a left-tailed. So the test statistic is 3.823. N is 13, so degrees of freedom would be 12. And it's a left-tailed chi-square test. Therefore, it would look like this. The alternative sigma would be less than a number, but the null sigma would be greater than or equal to a number. That's a left-tailed chi-square test for true standard deviation. We would go to row 12 and block it off, and we would find the 2 values that encompass the test statistic. And the test statistic again was 3.823. So that means the test statistic falls here. This time when you go up to the top, You don't have to cross fingers. When you're on the left side of the chi-square table, you do not cross fingers. You only cross fingers on the right side of the chi-square table. I know that sounds silly, but when you're on the left side, what I do and what you should do is I write the numbers that I see up at the top, and I subtract each from 1. 1 minus 0.99 is 0.01, and 1 minus 0.975 is 0.025. That means that your p-value interval, and you don't have to switch these around. You never have to cross your fingers. You just have to subtract each from 1. There's your p-value interval for this left-tailed chi-square test, where the test statistic falls on the left side of the table. Just go up to the top and subtract each from 1. 0.01 to 0.025. Do not switch those around. Again, if you're on the right side of the table, like we were just a few moments ago, we did switch our fingers around for that right-tailed chi-square test. But on the left side of the table, we subtract each from 1. Last problem. Number 8, last p-value interval problem. Find the p-value interval when the test statistic is 3.823, sample size is 13, and it's two-tailed. So that looks very, very similar to number 7. And I will write this information down. When a chi-square test is two-tailed and you're trying to find the p-value interval, I'll write down this information. Your test statistic is 3.823. Your sample size is still 13, so go to row 12. And we know it's a two-tailed chi-square test. And if it's for standard deviation, it looks like this. Sigma equals a number, sigma does not equal a number. You will go to row 12, just like we just did. And we know it's two-tailed, and you will block it off. Find the two values that bound your test statistic, which is here again, 3.823. Go all the way to the top. Do not cross fingers. Write those values down and subtract each from 1. So 1 minus 0.99, 1 minus 0.975. We got 0.01 and 0.025 when it was a left-tailed, like in number 7. But the next step, if it's a two-tailed chi-square test, then you would just double. So your p-value interval for problem 8 is that your p-value is somewhere between 0.02 and 0.05. You double. Not only do you subtract from 1, but then you double. When it was a left-tailed, this is what we got in number 7. But as a two-tailed, same test statistics, same degrees of freedom, double each. So 0.01 times 2, 0.025 times 2. Therefore, the p-value is between those two values. And I have a summary I would like to say about these p-value intervals. Basically, if your test statistic falls over here on the right side of the table, and it's a right-tailed chi-square test, you go to the top, cross fingers, and that's your p-value interval. If your test statistic falls on the right side of the table, and it's a two-tailed chi-square test, not only would you go to the top and cross fingers, but after you cross your fingers, to remember which one goes first, in this case 0.005 goes before 0.01. After that, if it's a two-tailed and you're on the right side of the table, you would double each of those. Now, the left side of the table is different. If it's a left-tailed chi-square test, then you just go to the top and subtract each from 1. Do not switch them around. That's your p-value interval. If it's a two-tailed chi-square test and your test statistic falls on the left side of the table, you go to the top, first subtract each from 1, and then after you subtract each from 1, you double. You never switch them around on the left side of the table. Hope that kind of summarizes the different situations, the right-tailed, the left-tailed, and the two-tailed. The tricky thing is if it's two-tailed on the right versus two-tailed on the left. The test statistic falls on the right and it's two-tailed. The test statistic falls on the left and it's two-tailed. So you have to remember that step of doubling. Cross fingers and double, subtract from 1 and double, basically, if it's a two-tailed test of any type of chi-square test. Problem number 9 is raw data. The p-value method. A researcher knows from past studies that the standard deviation, the time it takes to inspect a car, is 16.8 minutes, and is means exactly equals to. A sample of 24 cars is selected and inspected. The standard deviation of that sample is 12.5 minutes. At alpha equals 5%, can it be concluded that the standard deviation has changed? Assume the variables normally distributed. With this example, it's actually a two-tailed chi-square test. And I'll write down the information. A researcher knows from past studies that the standard deviation of the time it takes to inspect a car is 16.8 minutes. In a sample of 24 cars that was selected and inspected, the standard deviation S turned out to be 12.5 minutes. At alpha equals 5%, can it be concluded, so here's the claim, what we're testing, that standard deviation has changed, and you have to think about has changed from what? Has changed from the 16.8 minutes. Standard deviation of sigma has changed means not equal to. So there's your claim. The researcher at the beginning says that the standard deviation it takes to inspect a car is 16.8, but they take a sample of 24 cars and find the sample standard deviation is 12.5 minutes. At alpha equals 5%, can it be concluded that the standard deviation is no longer 16.8? It has changed from 16.8 minutes. And the first step, this is the p-value method, is the setup. You have sigma equal to 16.8 and sigma does not equal 16.8. And the claim is the alternative. Has changed means not equal to. Step number 2 is the test statistic. And that's going to be 24 minus 1 times s squared. This time you will have to put in the s and square it. They did not give sample variance. They gave sample standard deviation. So you'll have to square that s. Also, the claim is 16.8 as a standard deviation. Has changed from 16.8. So in the formula, you'll have to square it. Pay attention to what they give you. They don't give you s squared, so you will have to square it. They don't give you sigma squared as the claim. They give you sigma, so you will have to square it. And the test statistics should be 12.733. And it's positive. Then the p-value interval. Your test statistic is 12.733. Your sample size is 24, so you go to row 23. And you want to go across that row and find the two values that bound your test statistic. So 12.733, row 22, row 23. And the test statistic is between 11.689 and 13.091. Your test statistic. 12.733 .9733 was the test statistic. We are on the left side of the table, so we'll go to the top, and I'll write down .975 and .95. Subtract each from 1, and you get .025 and .05. If it happened to be a left-tailed test, this would be the p-value interval, but since it's a two-tailed test, you would double. And this is what you would get. Your p-value is between 5% and 10%. So double because it's a two-tailed. Now, decision time. I'm going to go back to the work and write this down. Step 4. P-value. The TI-84 does not have a program that will calculate a specific p-value unless you download the program from the CD that came with your textbook. So we will only be able to use the interval. And think about it this way. It's somewhere between .05 and .1. And even though it's not money, if you think about pennies, 5 cents and 10 cents, so it could be 7 cents, 8 cents, 9 cents, 9.5 cents, 7.25 cents. It could be anything in between. And when I say that, 7 cents, it would be .07. 9 cents would be .09. But it's not money, but a nickel and a dime. Anywhere between a nickel and a dime would be the possible p-value. Compare alpha box possible p-values between a nickel and a dime. Alpha was given to be 5%, which is a nickel if you think about money. And we know that the p-value is larger than a nickel but smaller than a dime according to the interval. Therefore, the p-value is larger and alpha is strictly less than. Any possible p-value here, which could be .07, .08, .09. So alpha smaller. Therefore, do not reject the null statement that said the standard deviation was equal to 16.8. The claim was the alternative that says it has changed from 16.8, and we're not rejecting the null. There is not enough evidence to support the claim that the standard deviation has changed from 16.8. There's not enough evidence to support the claim. If you need to see your diagram, again, the claim is the alternative, and we do not reject the null, so we're here. There is not enough evidence to support the claim that the standard deviation has changed from 16.8. And there you have it. You have your p-value interval, your p-value method here, and you're able to compare and contrast alpha and p-value to make your decision and therefore your summary statement. And I've practically finished the entire sheet 1 through 9. The next Tegrity lecture and final Tegrity lecture will pertain to the practice test, where I do everything together, the z-test for the mean, the t-test for the mean, proportion z-test for true population proportion, and chi-square testing for true variance and true standard deviation. You need to continue to practice outside of class in order to prepare for this test. A lot of students find that the chi-square testing is the most difficult because of how the chi-square table operates, especially when it comes to the p-value intervals for a right-tailed, left-tailed, and two-tailed test. But I hope that with these few examples, you'll be able to understand how to calculate the critical values and the p-value intervals from the chi-square table. God bless you, and I will be making the practice test available very soon.